All right, next door, can you hear me? Yeah. All right, thank you. Good. All right. Okay, so before we get going, first thing is I've uploaded your next so-and-so assessment. It's due this Sunday, so back to doing those until the next test. Now, I must apologise with the stuff up with the test venue. I was told that whoever's in frickin' charge of this stuff, so you notice that all the rooms have this sign in them that tells you the room capacity. This is a lie, right? They told me that they are accurate, they're not, as we discovered the hard way. The capacity of Tattersalls and Willsmore was 460 according to these things. This class is 430. There should have been enough room. As we saw, there wasn't, right? So it wasn't by a mile. So I know that some people had to sit uncomfortably. I do apologise. I was informed that the capacity was, I knew it would be tight, but I was informed it will be fine. Obviously, it was not. I do apologise for that. Obviously, being the weekend, I couldn't get another venue. Everything's locked. So for the next test, I will have a third venue. I'll make sure there's a third venue, and I'll tell you where to go based on your surname, all right? But I am very sorry about how, for the people that had to sit down the front, I do apologise. I was told it was enough room, and there wasn't. So it's my stuff up. I'm sorry about that. I'm sorry it was a bit full, okay? The tests, I've given it out to my markers, so I've told my markers I want the test marked and returned to be my next Friday. So what's that? That'll be, so in week, what are we in now, 6? In the practical classes in week 8 is when you'll start getting your test papers back. When they're actually marked and physically returned to me, I'll send out a message, I'll upload a copy of the test paper and solutions, and up to Blackboard so you can check your working and stuff like that. Until that happens, I don't physically have them. So we use a system called CS Marks to record your marks. You might have seen the link already in Blackboard. Your mark might appear there because my markers might enter as they go, but until I send the email out, I don't physically have the papers in my possession yet, all right? So before you start asking questions about your mark, wait until I've sent the email out, okay? Is that okay? Yeah. What do we think of the test otherwise? Good or bad? Oh, thumbs up. Oh, that's pretty rare. All right. Again, I do apologise about the people who had to sit down the front. I'm sorry about that. I mean, they told me doesn't matter. This stuff really annoys the hell out of me. But they said holds 460 comfortably. Bullshit. So anyway. It won't happen for the second. For the second test, I'll have a second venue, okay? Again, I do apologise for that. I'm very sorry. I know there's nothing worse than trying to do a test on an uncomfortable desk. You know those rooms where you get the desk that swings up the side? Yeah? I fucking hate those rooms, thing. Yeah, and having to do, well, back then I was a lot bigger, back then. I was bigger. And I used to hate doing, there's nothing worse than doing a test on an uncomfortable seat. My pet hate is when the frickin' table rocks. Like, I always bring a spare piece of paper when I go to a test and shove it under there. Anyway, I do. It's my fault. I do apologise. I'm very sorry about that. Okay. Any other comments about the test besides the crappy seating arrangement. Are you freaking kidding me? Next door, can you still see me? Yeah. Thank you. Yeah, any other comments about the test? No, all good? Okay. All right, yeah. Anyway, sorry about the stuff up with the room, but anyway. All right, what we're going to do, not this lecture, but in the second and the third lecture this week, we'll spend the next couple of weeks doing integration. So, and in particular, integration strategies. The first thing we're going to do, though, is something called Taylor polynomials. And when you do Math 101-2, you will learn about infinite series. And then there's something called a Taylor series. And what we often use them for, one of the main uses of them is integration, or within integration, because we all should know what an integral is, and so I expect everyone knows what an integral is and has done what I call integration by basic substitution. By basic, I don't mean easy, I mean the substitution's obvious from the question. We all should have already have done all of that. The problem with integration, remember what I said about differentiation though, as long as you've know how to differentiate the most basic functions, you know and understand how to apply the product, the quotient and the chain rule, you can differentiate anything I give you, no matter how complicated. Right? And that's true, hopefully. Integration, however, which is the opposite of differentiation, does not always work. That's what makes integration, although it's the opposite process of differentiation, that's what makes integration so bloody hard, right? Because it can't always be done. And there's a great comic which basically summarises what the hell's going on, right? So you look on the left. Left is differentiation, yeah? Try applying the chain rule, the power rule, which is derivative of x to the n, basically. That's what they call it in the United States. Chain rule, product rule, quotient rule, done. No, try again. Right? As I keep saying, there's nothing else to do with differentiation. However, you look at the one on the right for integration. Right? The point of this comic is integration is nasty business. Right? Try applying integration by parts or a substitute. We're going to do all of these. And you can see there that, no, lots of question marks. Install Mathematica, which is like a computer algebra system that'll do the work for you. Phone calls to mathematicians. Burn the evidence, The point of this is that this is the problem with integration. It can't always be done. And when I give you integration questions, it is very easy, right? I make absolutely certain this doesn't happen, but it's very easy for me to accidentally give you an impossible one, right, that can't be done. I want to illustrate this with something. Let me just, we're going to cover all of this in the next couple of weeks. Let's have a look at these four integrals. All right. Now, I expect at this stage everyone should be able to do the first one and the third one. Yeah? Right, the first one's basically straight off the formula sheet. The integral of e to the x is just, right, because the derivative of e to the x is e to the x. Yeah? The third one, hopefully everyone recognises that's a simple, what's called a simple substitution. We're going to review all this in the next lecture, so don't stress too far so far. The second one we can do using a technique called integration by parts, which we'll learn about soon. That one's, we'll find out later on, is that. Right? Fourth one, impossible. Can't be done. Right? So the first thing about integration is read the question carefully. If you accidentally write down the wrong thing, right, you could end up basically you could end up in that situation, right? Because that's the trouble with integration. It can't always be done. So when this happens, and this happens a lot, so when this happens and mathematicians get integrals that they can't do, like the fourth one, we invent a new function. That's the answer, right? So the fourth one is a function called the error function. So this one can be integrated. It's something like that. It's something to do with the error, a function you haven't heard of, right? And so a lot of the time we invent new functions for the sole purpose of finding an integral we can't find, right? Of being able to do an integral we can't find, right? So I think I've explained to you before, there's basically three types of mathematicians. There's pure mathematicians, applied mathematicians, and statisticians. So statisticians obviously do statistics, pure mathematicians do proof and very abstract stuff, applied mathematicians use math to model the real world, mostly with calculus. That's what I do. All right? And every applied mathematician has a book. Almost every applied mathematician have this book. It's called The Handbook of Mathematical Functions by Ambrowitz and Stegen. I might bring it on to the next lecture. It's in my office. So it's about this thick, and it's a book full of formulas of functions. It's got about 30 odd chapters. Chapter 1 is exponentials, logs and trigs. So the remaining 29 chapters are functions like this that you've never heard of, right? So if you look at this comic, for example, this is a classic one because lots of integrals involve Bessel functions. So you'll notice one of the things here, what the heck is a Bessel function, right? Lots of integrals involve this thing called the Bessel function, which is in this book, right? But you might think, well, you're just inventing a function. We're not really just picking it out of thin air. We study its properties by finding its Taylor series representation and then looking at what it does and where it converges and things like that. So Taylor polynomials and Taylor series are used, basically you can use them to turn a function into a sum involving powers of x. Right? And sometimes the approximation will be really good, sometimes it'll be really crap and you need lots of terms, but usually we can make it work. And because it involves just x to the n, that we can always integrate, right? Because the integral of x to the n is x to the n plus 1 over n plus 1, right? So a lot of the times we use Taylor series and Taylor polynomials to handle integrals we can't do, right? So in this unit we're just going to review Taylor polynomials, and when you do Math 1012, you'll do Taylor series, where you'll learn actually how we can use them to approximate functions to any accuracy we want. But because we don't do infinite series until Math 1012, we're just going to do Taylor polynomials first. And it basically extends the idea of a tangent line and a tangent plane, right? So we'll call it, when we've got a function of a single variable, say y equals f of x, we can easily find the equation of a tangent line. Right? So y minus f at c is the derivative of f at c times x minus c. Right? And you see that, well, if I wanted to use that to approximate this function, obviously near c it's all right, but move away from c it's rubbish, isn't it? Depending on what the function's doing, right? But you can sort of see if you're close to see it, that's a decent approximation, isn't it? If you sort of zoomed in, you know? Right, and here's an example of, of finding the equation of a tangent line to the parabola at x equals 3. So you can sort of see, say between x equals 2 and 4, it ain't bad. It's not great, but it isn't bad, right? And the closer we are, of course, at 3 it's exact, right? It matches exactly. And you sort of imagine that near 3, it's a decent approximation. Yeah? And for functions of two variables, well, the analogue of the tangent line is the tangent plane. So here, for example, if we've got this surface, this is the equation of the tangent plane. If I plot them both, so the red is the surface and blue is the tangent plane, you can sort of see at the point, what was it, x equals, was it minus 1 and 2? Yeah, at x equals minus 1 and y equals 2, it's exact. And if you're sort of near enough to it, it's a decent approximation, isn't it? All right? So we call the tangent line and the tangent plane the best linear approximation to a function at a particular point. Right, but sometimes linear is not enough. I mean, you might think, well, you know, for this one, for example, like well, it's a quadratic, but if you, let's say it's not a quadratic, that's just some curve. A quadratic would probably be a better, you could go a bit further away, couldn't you? Right? It would start taking into account the curvature of the thing. Maybe you could use a cubic, that would be better. You know, obviously not for a quadratic, but for some other function, it would be better. So what we basically want to do is be able to use polynomials to a certain order to approximate a function at a particular point. These we call Taylor polynomials. And when you do 1012, you'll learn about Taylor series, how we can define the whole thing in terms of an infinite series, a Taylor series, provided it converges. You'll learn all about that in 1012. All right? So sometimes linear is not enough. If we want a better approximation, how can we do it? Well, we use the concept of a Taylor series. Now we'll go through the function of a single variable first, right? And then we'll do the one for several variables, which gets rather cumbersome when you get past the quadratic term, but we'll get to that in a moment. Let's say we've got a function and that it's a function of a single variable and all of its derivatives exist, right? Then by definition we say that the nth degree Taylor polynomial approximation of that function is given by this expression here. So you'll notice the pattern. It's, you know, the function at a plus the derivative of the function at a over 1 factorial times x minus a plus the second derivative divided by 2 factorial times x minus a all squared plus, and of course the dot 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 means, and so the pattern continues. And up to order n, the nth term, the last term you want, will be the nth derivative of the function evaluated at a divided by n factorial times x minus a to the n, right? And of course here we're using the shorthand for factorial notation. So n's always an integer, of course. So factorial notation, so 4 factorial is 4 times 3 times 2 times 1, and 10 factorial, 10 times 9 times 8 times 7 times, you know, you get the idea. Now, the nth degree Taylor polynomial of a function is a polynomial up to order n. It doesn't necessarily mean it's going to have n terms. Some of the terms might be 0. That happens a lot, especially with the trig functions sine and cos. Okay? Now, how is this working? Well, you'll notice that if I evaluate the right-hand side at the point x equals a, you know, all the terms from the second term on are all 0 because they all involve x minus a, right? So the value of the Taylor polynomial at a matches the value of the function at a. If I now differentiate the right-hand side with respect to x, right, the f of a is a constant, that's 0. The derivative of the first term is just basically f dash at a. Right? And so that tells you the derivatives match at x equals a. Right? And if I do the second derivative, then the first two terms then disappear because the second term is basically x to the power 1. You differentiate that once, it becomes a constant. Differentiate the second time, it becomes 0. Basically, the second derivatives will be f double dash at a. So all of the derivatives match. This is where this formula actually comes from. Right? And you can see, where is it? It must be in the unit reader, but basically that's where the formula comes from. I give you this formula on the formula sheet, so you don't have to memorise it. We've just got to use it. Okay. So in most questions you'll be given n and a. The point so this notation is this is the Taylor polynomial of order n about the point x equals a of some function f of x. Right? Notice that the Taylor polynomial of order 1, which is one where I'd stop there, is precisely the equation of a tangent line. Right? That's the equation of a tangent line. Right? What this does is add corrections so that makes the approximation better as you move further away from the point x equals a. For the special case where it's a Taylor polynomial about 0, right, then the formula becomes even simpler, right, because all the x minus a's just become x's, basically. This is sometimes called a Maclaurin polynomial. So Maclaurin and Taylor are mathematicians. So Maclaurin came up with this idea first, but only looked at expanding functions about 0. Taylor extended it and then filled in all the gaps. about things like remainders and how good it is and things like that. So, right, but a Taylor polynomial about 0 is sometimes called a Maclaurin polynomial. Let's have a look at an example. Let's say we've got the exponential function, right? Now, before we get to this, remember in this unit you're only allowed to use scientific calculators, which have been around forever, you know? Well, not forever, you know what I mean, right? But believe it or not, calculators are pretty dumb. All they can do, believe it or not, all a calculator can do is add and multiply. That's all it can do. That's all its tiny brain can actually handle. All right? So if you ask your calculator what is 3 minus 2, your calculator interprets that as what is 3 plus of minus 2. Right? Because all it can do is add. It can't subtract. Right? It turns subtraction into addition. If you ask your calculator what is 3 divided by 2, your calculator interprets that as what is 3 times a half. Okay? Because all it can do is add and multiply. And of course then we ask our calculator, well, evaluate exponentials, logs and trigs at particular points. Have you ever wondered how it actually does it? Right? If all it can do is add and multiply, how the hell does it calculate e to the 37 for me? Right? It does it because it has a Taylor polynomial approximation of the exponential function in its memory. Right? So for example, it might have, for argument's sake, it might have the last one. It might have a 5th order Taylor polynomial approximation of e to the x. So when you ask your calculator to evaluate e to the 0.5, what it does is it says, well, that's 1 plus 1 times e to the 0.5 plus a half times e to the 0.5 times a half times 0.5 times squared plus a 6th times 0.5 cubed plus, and that's what it's doing. It's just multiplying and adding. Right? Because this is the power of Taylor polynomials. You turn a function into powers of x, which we can always handle. We can easily evaluate them, and we can always differentiate and, in particular, integrate them. So if it turned out we couldn't find the integral of e to the x, this is how we could at least approximate it and get a feel for what the integral is. Right? Now, for this exponential function, I want the Taylor polynomial approximation of e to the x about x equals 0. Now, this one is the easiest one to find because all the derivatives of e to the x are just e to the x, right? So if I asked you what is the 1/1,000,000th derivative of e to the x, it's e to the x, right? Because there's no function easier on the planet to differentiate than e to the x, right? So all of the derivatives of e to the x are that. So the nth order Taylor polynomial is just this. Right? It's 1 plus x on 1 factorial plus x squared on 2 factorial plus x cubed on 3 factorial plus x to the 4 on 4 factorial and so on. Right? So here I've listed the first five. Right? So the first one is basically the same thing as that's the equation of a tangent line, t to the x at x equals 0. Second order, that's a quadratic approximation, then a cubic and a quartic and a quintic. Right? And you can see here I've plotted them all. So the red one is e to the x, you know, and you'll notice that as they get higher, you can concentrate on the point x. For each one, you can move further away from x equals 0 and get a more approximate answer. So this is how your calculator calculates e to the x. Now it does some other clever tricks. There is a trick where you can expand it about whatever point you like. So if you ask your calculator to evaluate e to the 10.4, what it will do is it knows how to calculate the Taylor series expansion of e to the x about x equals 10, right, and then use that one, right, because then 0.4 is not far away from 10. That's basically how your calculator does it. And with logs and trigs as well. Right? But you can sort of see that as the order goes up, they get better. I mean, so the order 5 one, I mean, even out this far, that's about x equals 3. It's not bad. It's obviously absolutely shocking over here, right? But you sort of see there's a sort of a window around here where it's a decent approximation, right? So we can use it as long as we're careful not to move too far away from the point we want. If I wanted to be more accurate, I just use more terms, right? I mean, it turns out the Taylor polynomial of the exponential function up to order about 50 is awesome. Right? It'll calculate e to the x to basically something like 10 decimal places. right? Which is more than enough for your calculator, for example. Right? Now here I've got how it approximates at x equals 0.1 and 0.5. So you can see at 0.1, here I'm using the particular order of the Taylor polynomial to calculate an approximation to e to the x at x equals 0.1, the actual value of e to the x, and the error. Right? So you can see when I'm very close, I mean, the third order Taylor polynomial gives me an answer correct to 5 decimal places. As I move further away, I need more terms. Right? But it will get there. I mean, even at order 5 up to 0.5 distance away is correct to 4 decimal places. Right? Right, so what we often use them for is to approximate functions. Now, back before calculators, this is how depending on how old your parents are, when they didn't have calculators at school, they would have had a tables book of functions, and they would have used Taylor series to do it. Right? These books were calculated using Taylor series. Obviously, nowadays we have calculators to do it for us, but the point is, back in the day, we used to use these to approximate functions. What we use it for mostly now is to work out integrals that we can't generally do. Right? But of course, there is an error involved. Right? And this is the work that Taylor did that extended what Maclaurin did. Maclaurin just used it as a tool and didn't really think about how useful it was. So Taylor looked at things like, well, how good is it? How many terms do I need? Well, if you ask the question, well, let's say I've got something that I can't use in the normal sense, so I want to use a Taylor polynomial to approximate it. The question Taylor asked himself was, well, how many terms do I need? Right? If I want to approximate this thing to, say, 3 decimal places, how many terms will I need to make sure it's good enough? Or if you're constrained to, say, use an order 3 polynomial, how far away from the point I'm expanding about can I go before it starts being rubbish? Right? So this is what Taylor looked at. So Taylor polynomials can be used to approximate, but of course it is approximate. They're not exact. Right? The only time they're exact is when you use a Taylor polynomial to approximate a polynomial, which is stupid. Why would you bother? You've already got a polynomial. Why would you want to approximate it by another polynomial? Right? But if you wanted to, you could, I suppose. Waste of time, but anyway. Right? So there is an error involved. Right? So the function approximately equals its Taylor polynomial. Right? But in actual fact, it will equal its Taylor polynomial plus an error. What I want to do is be able to estimate the error. Right? So the following theorem gives, so we say a function equals its Taylor polynomial of order n at a plus some remainder term of order n at a, right? The Rn bit, right? And the following formula gives you a way to estimate the error. There are 2 ways you can do this with functions of a single variable. It's called Taylor's formula, or there's Taylor's formula in Lagrange form, which is the one I'm going to show you because I find that one easier than the other one. The other one uses supremums and infinims, and that's pure math stuff, and I don't want to worry about that crap. I've forgotten all that. Not really, but I don't want to use it. Right? So the following theorem is an approximation for the error. Now this is proved in the unit reader if you're interested. Right? It's not pleasant, but it is in there, right? If you're interested. But if you look at it, it kind of makes sense. If we go back here, right? Let's just have a look at this one for the not that one, sorry, this one. Right? Let's say I've used an order n polynomial. If I want to estimate the error, what I want to know is, well, how big is the next term I'm dropping? Right? That's basically what you're asking, isn't it? What's the next term? How big is it? Yeah. Right, so the next term would be the nth derivative, the derivative of the function, the n plus 1th derivative of the function over n plus 1 factorial times x minus a to the n plus 1. That's the next term I'm dropping. Right, so I want to try and estimate the size of that term, and you can see there that's what that term is doing. Right, so the remainder is you're trying to estimate without actually calculating it. You're trying to estimate the size of the next term you're dropping from your Taylor polynomial approximation. Right? So notice there's a z in here. This is your choice, right? What we generally do as a rule of thumb is we try and pick a z such that the error is as big as possible, worst case scenario. Right? So if there exists some z, and it'll be between the point you're expanding about, and it's basically between the point you're expanding about and how far away from that point you want to go. Right? And z is free for you to choose. And what we generally do is we choose it so the error is as big as possible. So there's two reasons I prefer this one to the other one. This one always overestimates the error. This is worst case scenario, which is always better than, you know, in the error term you get from this one, it can't be any bigger than that. Right? This is absolute worst case scenario. That's why I prefer this one. Right? And I say it's proved in the unit reader if you're interested. Right? And to make the error as large as possible, we pick a z such that the derivative is as large as possible. Let me show you how we often use this. Let's look again at the Taylor polynomial for the exponential function about x equals 0. Right? So we've already shown that that's what it looks like. And at a particular order n, that will be the remainder term. Right? So the remainder term will be e to the z over n plus 1 factorial times x to the n plus 1. So the n plus 1th derivative evaluated at some point I choose. Right? And the only restriction on z is it's somewhere between 0 and x. It's like a measure of the distance. How far away from the point I'm expanding about can I go? Right? So technically z's got to be between minus x and plus x. So minus x away from 0 or plus x away from 0. Right? And I've got to choose a z somewhere in there. Now what choice of z should I make to make this as big as possible? Well, I know the exponential function just keeps growing for positive x, don't I? In the positive direction it just keeps going up. So the absolute worst value this could take would be when z equals x. Right? When you're calculating it as it rises. Right? And that'll give you the worst case scenario. Right? Right, so since e to the x is an increasing function, the largest value this can take between minus x and plus x is z equals x. Right? Now, once I've figured that out, I can use this two ways. You can either use a given n find x, or given x find n. Right? So in other words, I could say, I want to use a third order polynomial. How far away from x equals 0 can I go such that the error is decent to however many decimal places? Or I could say, I want it to be accurate this far away to this many decimal places. How many terms will I need? So you either can use this to find x or find n. Right? Depends on the question. Right, so here the remainder is, let's say I want to know how many terms of a Taylor polynomial I would need to approximate e to the x at x equals 3, so that's a fair distance away from x equals 0, to an accuracy of, say, 1 decimal place or 2 decimal places. So the error I want it to be less than 0.01. Right? So in other words, I plug in x equals 3 into my remainder formula, and I want that to be less. I want to find the value of n such that that is less than 0.01. Right? If there's negatives in there, these are errors. You just take the absolute value and just make them positive. Now, obviously, that formula, e cubed is just some number. 3 to the n plus 1 over n plus 1 factorial, you can't solve that. That's impossible to solve. Right? So these ones where you do trial and error. Right? Obviously, because of the factorial, it will keep going down as n goes up. So you remember when we were doing L'Hopital's rule, and I said nothing grows quicker than the exponential function? This is the only thing that grows quicker. The factorial function grows insanely fast, right? But it's not a function in the usual sense, right? Because we only use it for integer values, right? So it's like a function whose domain is only positive integer, so it's not continuous, it's a bunch of points. You can join the dots together and turn this into a function. We call that the gamma function. It's in my book. It's one of the chapters in my book. And you can find, there are things like, what is factorial of a half? Right? Now, that doesn't make sense when we think of the factorial the way we normally use it, right? But you can turn it into a function, right? But this can't be solved for us, so we just do it by trial and error. So you just start with some values of n. Obviously, I've cheated and gone to the answer. So when n equals 11, I calculate that the remainder term as a worst case scenario, because I've picked the z to make it as worse as it could possibly be, is 0.0223. That's not quite good enough yet. But n equals 12, good enough. Right? So a 12th order polynomial is what I would need. So this is saying that you can calculate e to the x anywhere from x equals minus 3 to x equals plus 3 with a 12th order polynomial, and the answer will be accurate to 0.01. That's basically what this is saying. Right? So you imagine though a 12th order, I mean that's the 5th order. You can imagine this all the way out to x to the 12, right? But you know, computers can do that for us. They can calculate that for us, an order 12 polynomial. On the other hand, we could use this another way. Let's say for some reason you are constrained to use a quadratic approximation, right, for some reason, right? So those of you who are doing engineering, I don't know if you all do it, but a fair chance, who's doing civil and mechanical, right? You people will do something called finite element modelling, which is a way we can use to model the real world using an approximate answer. And the way you do finite elements is you use quadratic approximations to the functions on tiny pieces of the domain. Right? So that's a case where you're constrained to use a quadratic, and the domain's got to be small enough so that its Taylor polynomials are good enough, right, to give you a decent, and then it just stitches them all together. And obviously a computer does it. We don't do it by hand. That'd be insane, right? But let's say we're constrained to use a second order polynomial. How far away from 0 can I move such that this is going to give me a decent answer? Probably not that far, right? But how far? For what values can let's just look at the right-hand side. Is this thing going to be accurate to 0.01? So this question, it was given x, find n. This one is given n, 2, find x in this case. Right? So I go back to my remainder formula. Now I plug in n equals 2 and I use this to solve for x. Notice that one also can't be solved for x. Right? E to the x times x cubed, you can't actually solve that for x. Right? I can, but you can't. It involves a function you haven't heard of. That would be would be frickin' awful. It would involve the complex branch of the Lambda. Ugh, no, that'd be awful. But I could do it, right? Not that I would. I'd just do it by hand. I'd just guess, right? But by trial and error, you can find that you can go as far as 0.34, so pretty crappy, right? And by symmetry, you could make it go both ways, right? So either x is between, you can basically, it's like how far, this 0.34 is, how far away from 0 can I go where the answer's accurate enough? And this isn't very good, right? But it might be good enough. If you only want the exponential function very close to 0, this might be good enough for you, right? But this remainder formula will give you an idea of how far you can move, okay? Right, so I've got some examples in here. All right, let's have a look at the log one. This is also actually how you calculates a logarithmic function. All right? Let's find the third order Taylor polynomial of the logarithmic function about the point x equals 1. All right? So obviously, what if I asked instead, find the third order Taylor polynomial of log of x about x equals 0? What's the problem? The series can't get started. The first term of the series is the value of the function at 0. Log of 0 is undefined. It's minus infinity, basically. Right? So then it's not going to work. Right? So this one's at 1. I've done this one at 1 instead. And then for what values of x greater than 1 is this third order polynomial accurate to 2 decimal places? The way I usually attack these is, well, I need a third order Taylor polynomial, so I need the first 3 derivatives. Right? Now, obviously, I'm not going to be stupid. I'm not going to I'm not going to give you a question and say, find me the 27th order Taylor polynomial. Come on. Right? I'm not going to ask you to do that, unless it was the exponential function, because then that one's easy. All the rest are terrible. Right? But I need the first 3 derivatives. So derivative log of x, 1 on x, then second derivative minus 1 on x, third derivative 2 on x cubed. I evaluate them all at the point I'm expanding about, and I just plug them in the formula. All right, so the formula tells me, and remember, this is on the formula sheet. You don't have to memorise this. All right, and basically you just, where is it? right? You just, not that one. You just plug everything in here, right? So in this case, n is 3, a is 1. You've calculated all the, you just plug it in, right? All right, so it's f at 1 or log at 1 plus 1, the derivative of log at 1 over 1 factorial times x minus 1 plus the derivative of log at 1 divided by 2 factorial times x minus 1 all squared, and so on. All right? And then just clean it up. Now, that's good enough for me. Don't, usually I say you've got to expand and collect like terms. Not in this case. All right? That's fine. All right? That's perfectly fine for me. All right? Especially if I ask you an order 6, I don't want you sitting there freaking expanding out x minus 1 to the power of 6. Anyway, that's a third order Taylor polynomial. Now, the next one is now I want to estimate the error, right? So the next term I'm not taking into account would be the fourth term, wouldn't it? If I'm using a third order, the fourth is the one I'm missing, So the n plus 1, the next one, right? So the remainder formula tells me that it's the value of the fourth derivative at some value z that I am free to choose, and I choose it so the error is as worse as possible, over 4 factorial times x minus 1 to the 4. Right? That's got to try and estimate the size of this term that I'm missing. Now, if I calculate the fourth derivative of log, I get the fourth derivative evaluated at x is minus 6 on x to the 4. Yes?
Is that only for the positive values? Because you could just set it negative after, right?
Yeah, but because it's an error of plus minus, right? So you just ignore the sign, right? But that's a value of the fourth derivative. So what value of z between 1 and x would make that the biggest? Be 1, wouldn't it? Because anything else, it's a decreasing function, right? So I pick z equals 1 to get the worst case scenario, right? And notice I take the absolute value, right? So, error, plus error, minus error, they're still frickin' errors, right? Just think of it plus minus. Right, so I make the error as large as possible, then I need this to be less than 0.01. That's what the question said. How far away from x can I go? Right, if I solve that for x, I find 1.4, that one I can solve, multiply both sides by 4 and take the fourth root of both sides. I'd get, and then plus 1. I get x has got to be 1.445. So that's telling me I can only move 0.45 away from 1 to each side. Right? Any more and the error would be too big. Yeah?
Are there any cases where z isn't either x or the lower function?
It depends on the function, but most of the time it will be either the point or the most of the time they're either strictly increasing or strictly decreasing. Yeah, but it depends on the question.
Does the z always have to be between a and x?
Yes, yeah, and including a and x. That makes life easier. Yeah. Right. So yeah, the log one's a bit weird because moving to the other side is the log one's actually a bit more difficult to work with. But let's not worry about that. All right. Okay. So before we move on to we'll do this at the second order ones in the next lecture. What I'd like is please work through this example in the lecture notes with the exponential function, because the exponential function is the easiest one to do because its derivative is so well behaved. We know what it does. And also have a work through this one with the log function, and then we'll move on in the second one in function of 2 variables. Okay? But we'll leave it there for today, all right? And I'll see everyone tomorrow.